Thank you for joining me for this video on cylindrical shell templates, where we're looking at two generalized template forms, an excellent exercise which will help you understand and refresh the cylindrical shell technique. For the first example, we're looking at a representation which looks like this. We have this certain rectangular region which will now revolve or rotate around in the y-axis. How can you develop the template which will determine the volume of the resulting solid? You know, the volume of the resulting solid would look something like this. I'll just draw it out for you in a three-dimensional manner. It doesn't have to be anything too accurate, but we will try to do a good job here with regards to the drawing. And this is exactly what it would look like. The three-dimensional solid, as it rotates or revolves around the y-axis, here is your y-axis showing through. That's exactly what the solid is. For the cylindrical shell technique, you want to worry about the circumference, you want to worry about the height, and you want to worry about the thickness. But what are these things we're talking about? We're talking about the Riemann rectangles that you would use for this cylindrical shell template formation. This is my region of space, but each of these regions of space you can demonstrate it by means of rectangles which are a certain dimension away, which have a certain height. Here's my height and here's my radius. All of that comes into play, but you have a bunch of equations which you can develop. I'm just blowing it up. You have a lower boundary line which is y is equal to b1. You have an upper boundary line y is equal to b2. You have this side here, x is equal to a2. You have this side right here, x is equal to a1. All of these things will come into your template formation. In reality, you would have numbers here, but we're just using variables to express unknowns. What's my circumference? It's a certain radius away from my line of rotation, and that radius dimension here is equal to x. Therefore, circumference is 2 pi x. What's my height? Well, height is your top boundary curve minus your lower boundary curve. b2 minus b1. b2 minus b1. Now we have everything we need to develop the volume integral for the cylindrical shell template for this representation and for the solid. Since it's a cylindrical shell technique, things will flip around. Even though we have a rotation along the vertical line, everything here is with respect to dx. That's the way things work with the cylindrical shell technique. 2 pi, you have here this x, and then you have your height, b2 minus b1, and then you have your thickness. We need to have our intervals. What are our intervals? Well, everything is along the x dimension, therefore your intervals, lower and upper limit, must be these right here. And it'll be a1 and a2, and that right there would represent your volume integral, which would be the cylindrical shell technique or the template for this solid right here with a y-axis rotation. And this right here is our region of space which is being revolved around the y-axis. Now let's look at the next template generalization for this video. Now for the remainder of this video, we're looking at this last template formation. We're looking at a region of space which will now develop with a rotation around the x-axis. That's what it's going to be. But what will your resulting solid look like? Well, let's try to do a good representation for you. It will look something like this. And your x-axis is going to be going right here in between. That's going to be your three-dimensional solid as everything rotates. You're looking upward here in terms of your radius. But when you look at this rectangle, there are delimiting lines. You have y is equal to b2, upper boundary line. You have y is equal to b1, lower boundary line. You have here x is equal to a2, and then here you have x is equal to a1. When you're doing a cylindrical shell template for a region of space that's rotating, but with respect to x-axis, you're looking here now at a volume representation with respect to dy and y. You have to remember that. Your circumference here will have a radius component. The radius component here is a y. So it's going to be 2 pi y. Your height here is going to be now basically xr minus xl. What is that? Right boundary curve minus left boundary curve, which in this case will be this. a2 minus a1. That's what it is. And all of that comes into play right here. You have a 2 pi. Then you have your this right here. Y multiplied by your height, a2 minus a1 with respect to dy. Now we need our limits. What are limits? Are these upper and lower limits, but they're along the y-axis because everything here is with respect to y and dy. It'll be b1 and b2. And your cylindrical shell template for this representation with rotation on the x-axis has been developed. You would just carry this forward and you'll come up to your volume outcome when you have these unknowns determined, because here everything is variables and unknowns, nothing is concrete. We're just doing template determination and template derivation using cylindrical shell. That's all we're doing in this video, but the procedures have been laid out for you here, one with respect to dx, one with respect to dy, and that's it. Thank you for watching.